The premise of the ASHRAE Integrated Sustainable Building Design Competition is to design a zero-net energy building in Doha, Qatar. The building must be a 3-story junior college facility that satisfies both ASHRAE standards and building owner requirements. A zero-net energy building is defined as a building with an annual energy usage less than its yearly production of renewable energy. A major focus of the Integrated Sustainable Building Design Competition is to not only design a sustainable building, but to also expose students to a multidisciplinary collaborative design project. Designed between both engineering and architecture students, our project involved both sets of academic disciplines throughout the entire design process. Through a combination of sustainable building practices and alternative energy usage, our proposed building design reaches zero-net energy, while also achieving a LEED Platinum score. The energy consumption of the building was able to be reduced by 53.85% from the baseline model. The remaining energy usage is offset by an extensive photovoltaic solar panel array that was integrated into the design. Early in the design of this building, a benchmark was set by the design team to perform at least 50% better than the typical building in this region of the world. Compared to the typical building of this same size and function in Qatar, our building design is performing roughly 75% more efficiently and roughly 50% more efficiently than the calculated ASHRAE baseline model.
Because of the deep cultural roots in this area, we have chosen to design with cultural norms and values in mind. Many traditional Qatari buildings utilize a compact design, a close proximity of buildings, and central atrium spaces for passive daylighting and ventilation. Designs in this area often take advantage of this building typology for its inherent protection from climatic elements and its high levels of privacy. Traditionally, courtyards and shaded roof spaces have been used as areas to relax in the fresh air while being protected from the elements. We have utilized these strategies in our design as it has been tried and tested in the arid climate of Doha and allows a maximization of shading from the building surface. Our design incorporated an egg crate form with deep atrium spaces and has created a shaded rooftop terrace for additional community space. This terrace is shaded by a photovoltaic array to protect from the harsh sun and is accessed by the prevailing winds from the northwest for passive ventilation.
The site location that we chose is in the area known as the Education City. Education City is an educational district located on the outskirts of Doha. The site is proximate to many other standalone educational institutions within the district of Al Ghafara, and the extensive educational infrastructure already in place will be convenient and beneficial to the college facility. It is located near the highway, the campus light rail system, and adjacent parking structures, which will all allow for ease of transportation from other areas of the city, limit car traffic, and promote the Education City district. After researching the chosen site area, plans for an expansion and renovation of the city of Doha, as well as Education City, surfaced, reinforcing our site choice. The master plan of Education City outlines a reorganization of the existing circulation routes to and around the Education City and proposes a new light rail system. The path of the proposed light rail line delineates several axes of pedestrian transportation across the site and prescribes the optimal position for entry areas and courtyards for our junior college.
The site is bordered by a highway to the north and smaller access roads to the east and south. The hardscape of the site includes access roads, sidewalks, courtyards, and a small parking lot. Over 60% of the site hardscape is covered by native and biodiverse plants and trees located to provide shade, cooling, and sound isolation. The majority of the paving is made up through a combination of permeable paving and cool pavements. Permeable paving allows water to infiltrate through surfaces and return back to groundwater tables or surrounding plants and vegetation. Cool pavements work by improving sound intensity by 75 decibels. In combination with vegetation growth, the noise level and heat island effect will be reduced. Both of these also help in reducing storm water runoff and improve water qualities through proper pollutant filtration. Furthermore, portions of the roof will be covered in a green roof system of native vegetation. Our green roof serves several purposes, including increased insulation, rainwater collection, lowering of urban air temperature, and mitigation of heat island effect through evapotranspiration, and an increased quality of usable roof space.
Our exterior wall assembly was heavily influenced by the traditional building construction, the need for insulation from the elements, and the cost and availability of local materials. The total thickness of the wall assembly is just over 2 feet, with a total R value of 75.33. This high R value wall assembly will effectively insulate from the extreme temperatures in Qatar and will reduce the cooling load for the building. Evapotranspiration in the courtyards and on the roof will be used to passively cool, and cross-ventilation on the roof will be used to lower the temperature on the solar array. The solar panel systems in the roof area will also provide shading for the entire building, lowering temperatures and solar radiation exposure. Cross-ventilation in the building was heavily considered as the most effective option. However, design constraints prohibited operable windows.
Several mechanical cooling systems are implemented in our design. Hydronic radiant wall panels will be utilized because of water's superior latent heat capacity. However, since the response time of radiant systems is slower than that of traditional systems, an isothermal storage system has also been implemented. Isothermal storage is widely used in the Middle East. Careful considerations were taken to zone the building appropriately. The isothermal storage system will be used to condition the hallways, shop, computer lab, library, lecture hall, and larger meeting rooms. This system was chosen to condition these larger spaces because of the response time and cooling capability of the system. These spaces will demand a much larger cooling load due to the size of the rooms as well as the equipment that is utilized in these spaces. The isothermal storage system is broken into 3 primary zones: first, second, and third floor. Since cooling is the primary function that the system must utilize in this region of the world, the first and second floor will be able to utilize cooling from the floor above it as the cold air sinks down. This allows for a reduction in cooling load and energy use in the lower floors. Any heating needs for these zones that may arise can be addressed by the chilled beam ventilation system and its use of hot water. Radiant cooling panels will be utilized in the classrooms, offices, bathrooms, and meeting rooms because of the occupancy type and smaller cooling load needed. Radiant cooling panels have a quiet operation, which will be beneficial in the classrooms and offices, and they can also be easily switched to heating by setting hot water to the panels.
The photovoltaic system will be a lofted, roof-mounted, and fixed-tilt array covering the majority of the building's roof space. In order to prevent the solar panels from overheating, they will be lofted above the roof surface to maximize convective cooling. The electricity production of the solar array was calculated using the National Renewable Energy Laboratory's PV Watts program. Using an iterative approach from a DC system size, it was determined that a 261 kilowatt system would be required to cover the 465,839 kilowatt hours of energy usage. The PV system is expected to produce about 466,000 kilowatt hours per year, saving the building owner $32,636 compared to the typical building energy usage in Qatar. This system will save the building owner $256,529 a year. The cost savings when compared to the ASHRAE baseline is $119,623 a year. This system is expected to consist of 967 modules, totaling in $258,479 for this array. The payback period for the system is 10 years, and the total savings of the system based upon a 50-year lifetime is $4,591,754. Our proposed building design is 56.21% renewable energy, qualifying the building for maximum LEED credits in the renewable energy production category.
To reduce the need for electric source lighting levels as much as possible, daylighting strategies are implemented into the building design wherever possible. Where pure daylighting solutions are not practical, the LED and fiber optic lighting fixtures will be installed with accompanying occupancy sensors. We have chosen to orient the building on an axis 15 degrees west of north to maximize daylighting from the south and north while limiting harsh, low-angle light from the east and west. Along with this building orientation, the form is adapted to limit direct exposure through a shading analysis. This maximizes the amount of wall area that is shaded annually. We maximize shading by stepping out the southern facade to shade the lower levels from high-angle solar radiation, and stepping the northern facade back to shield from low-angle rays from the west. In addition to optimizing the building form and orientation, fenestration placements were given careful consideration. On the east and west facades, window placement has been restricted to the egress stair towers, as this light will be harsh with high solar heat gains. On the south side, fenestrations have been placed sparingly, keeping with our designated 15% window-to-wall ratio. Each interior space on the north and south side of the building receives lighting from one or more carefully placed window panels. To increase indirect daylighting in the building, we have placed 3 central atrium spaces that extend from the roof down to the ground floor. These spaces are enclosed by a glass curtain wall and allow high-angle sunlight to penetrate deep into the space. With our photovoltaic array on the roof, these spaces will be shaded from solar radiation, but will allow ambient light and bring a sense of openness into the interior of the building.
The annual energy consumption of the building was able to be reduced from 1,009,467 kilowatt hours to 465,839 kilowatt hours through a combination of efficient lighting fixture selection, day lighting, building material selection, and building occupancy scheduling. The selection of both passive and efficient HVAC systems also plays a major role in this energy usage reduction. The building's energy consumption is broken down into HVAC systems, lighting equipment, fans, and miscellaneous building equipment. As expected, the HVAC equipment uses the largest portion of the energy. The ASHRAE baseline model devoted 53% of the total energy usage to the HVAC equipment. The proposed building design utilizes only 34% of the total energy consumption for HVAC equipment, an improvement of 35.85%. This is accomplished through the reduced cooling load and efficient system selection. By reducing the energy consumption of the building, the energy use intensity units of the building were able to be reduced from 142.9 to 65.9 kilowatt hours per meter squared. Our building's EUI is still considered high for a net zero energy building. However, the climate of Qatar and the constant high temperatures have to be taken into account when evaluating this unit of measure. The cooling and heating load reduction is possible due to the heavily insulated wall construction that is proposed for this design. By implementing the suggested wall assembly, the building's overall cooling load will be able to reduce from 249.7 to 207.9 tons, an improvement of 16.74%. Likewise, the heating load will be able to be reduced from 71.2 to 56.25 tons, an improvement of 21.01%.
Our proposed junior college design has met the criteria outlined by the ASHRAE Integrated Sustainable Building Design Competition. Through a combination of sustainable building practices and alternative energy usage, our proposed building design reaches zero net energy and has achieved a LEED Platinum score. The energy consumption of the building was reduced by 53.85% from the baseline model, and the remaining energy usage is offset by an extensive photovoltaic solar panel array system.